Hey, I'm Yakov, and in today's video, I'm continuing my mini-series on protocols. Previously, I've covered the fundamentals of protocols in general and in Swift specifically. I realized that to some of you, those videos might feel too basic. But my goal is to create a complete guide to protocols. And besides, in the process, I learned about quite a few things myself. This time, however, I'm finally moving on to more sophisticated topics. They include protocol extensions, generics, and associated types. I'll explore why they exist in Swift, how they work, and how they can make your software design even more powerful. If you find this video helpful, don't forget to give it a thumbs up and subscribe to the channel. And with that said, let's explore the first topic for today. It is protocol extensions. Protocols in Swift are really powerful. I'd say they're much more powerful than similar tools in other languages. And the main reason for that is not even the core functionality of Swift protocols, but all the extras you can find in the language. Because, to be honest, it's pretty hard to invent something radically different in this area. I'd say the most prominent of those extras is protocol extensions. At first glance, they might look similar to extensions for other types, structures, classes, and so on. But in the case of protocols, they play quite a different role. Protocols with extensions are something like two-in-ones, the protocol itself and its own implementation. Here's how it works. In the protocol declaration, you list all the requirements of your protocols, properties, methods, the usual stuff. But then you've got a chance to implement some of those requirements right away in a protocol extension. In their syntax, extensions are really similar to the normal way of conforming to protocols. And unlike protocols themselves, extensions do expect you to provide method bodies. As a result, when it comes to conforming concrete objects to that protocol, they won't have to implement its properties and methods explicitly. Instead, they'll just be using the default implementations. If you want, you can actually implement all of a protocol's requirements in its extension. If you do so, conforming an object to that protocol will take just one line of code. Here's how it can help you. Let's say that your software design requires a certain behavior from its components. But implementing this behavior is straightforward enough, so it can be shared between all such components. In this case, if you provide a default implementation, you'll need to write its code only once, but all conforming objects will be able to use it. Of course, the conforming objects can override default implementations with their own versions. It's done the same way you implement protocol requirements in the first place. And unlike overriding methods and classes, you don't even need special keywords for that. In my previous video on protocols, I explained the core concepts of the paradigm called protocol-oriented programming. Well, protocol extensions and default implementations are the tools that largely enable this paradigm. If you remember, one of the key principles of protocol-oriented programming comes down to building small, reusable, and composable components. Protocol's ability to bundle default implementations allows the components to be truly small. They don't have a bunch of redundant functions dragging behind each time you implement a protocol. And of course, sharing a single implementation across all conforming objects makes mistakes less likely. Providing default implementations is the most interesting capability of protocol extensions. But it's not the only one. Besides implementing protocol methods and properties, protocol extensions can function just like extensions of other types. In them, you can declare methods and computer properties, and they'll be available whenever you use the protocol. Just keep in mind two important things. First, if you declare something brand new in a protocol extension, this symbol will not become a protocol requirement. As a result, the conforming object won't have a chance to provide its own implementation. And second, there are performance implications of declaring symbols like that. You might be surprised, but the protocol requirements are actually slower and more complicated behind the scenes compared to protocol extensions. Of course, we're talking about a difference that's entirely negligible in most cases, but it's worth keeping in mind anyway. In the next and final episode on protocols, I'll delve into method dispatching protocols and protocol extensions. This ain't something you think about very often, but knowing the key principles can definitely be helpful. So subscribe to the channel and stay tuned. In the meantime, let's have a look at the different ways you can declare protocol requirements. In the previous episode, where I explained the basics of Swift protocols, I mentioned that you can declare pretty much every type of member: properties, methods, initializers, and so on. I showed a few examples of methods, including throwing and async functions. But I saved one more kind for later. I'm talking about generics. Protocols in Swift offer full support for generic methods. You declare them the usual way, with angle brackets. Inside those brackets, you put the generic types. You can also specify some constraints for those types if you need them. Just as another generic context, the implementation must be able to take care of any supported type that you use. So for instance, if the generic type has no constraints, the caller can pass any parameter to the method. Then it's your implementation's responsibility to validate and handle all the possible values. Basically, generics and protocols look and behave just like they do in other objects. They allow individual methods to support more than one type as a parameter or return value. This ability makes your code more flexible, but without compromising its performance. And just like in other contexts, generics and protocols are resolved individually at the time of each function call. That means that different methods in a protocol don't know about one another's parameters. For instance, these two methods are supposed to work together, but technically they remain independent. Each of them supports the entire range of value types, and because of that, each has to validate and unwrap them individually. So, what can you do about that? What if you're building a system where different protocol methods do need that knowledge about each other's types? In that case, instead of generics, you can use associated types. Associated types in Swift are a tool that's exclusive to protocols. At first glance, they're similar to generics. The protocol declaration offers some sort of a placeholder, and when you use that protocol, you fill this placeholder with a concrete type. But if you dig a bit deeper, you'll discover that associated types are actually quite different from generics. First of all, they completely solve the problem with generics that I mentioned. When you declare an associated type, this single type is shared between all protocol requirements. As a result, different methods can rely on one concrete type. They don't have to employ defensive coding strategies such as typecasting, nil checking, and so on. But that's not the only benefit of associated types. Perhaps you know that generic methods are resolved statically when you call them. But associated types get resolved even earlier than that. When you implement the protocol, you have to specify the associated type explicitly. You can use a type alias for that. Or you can just replace the placeholder with your concrete type in method implementations. As a result, you know which values are fine and which aren't from the very beginning, even before you try to compile the code. And associated types aren't limited to being simple placeholders. They can constrain the types of objects accepted by the protocol. For instance, let's say you're declaring a protocol that's designed to merge two collections together. Obviously, merging two individual objects, like two numbers, it doesn't make a lot of sense. So in that case, you can restrict the associated type to only those objects which conform to the collection protocol. By the way, collection itself is another protocol with associated types. As a result, you can implement the protocol for two integer arrays, but you can't do the same for two integers. The compiler simply won't let you. Just to clarify, constraints like that work with generics too. The difference is that with generics, the restrictions are enforced when you call the function. But with associated types, you can even implement the protocol for your own type. This helps you to detect errors early in the process. Besides that, associated types provide a higher level of abstraction. What that means is they sort of fix type relationships in place and allow multiple protocol methods to work together. Once you've implemented a protocol in this manner, its associated type is already specialized. It can't be changed anymore. In other words, you don't have a chance to mess it up. You see, the more specialized your tools are, the more precise and powerful they can be in practice. And while it takes time to learn how to operate them, the results are typically much better than if you used a general-purpose tool for everything. It's like you can go to a store and buy a kitchen knife. It is good for many things, but if you were to perform a surgery, you better have a proper scalpel. Associated types and protocols highlight one of Swift's core principles. The language strives to move as many tasks as it can from the runtime to the compile time. This helps you make your software more robust, because the earlier your unknowns become known, the easier it is to find and correct any mistakes. And when it's possible, Swift goes even further and tries to make the unknowns known even earlier, just as you type in the code. That's the deal with associated types. However, protocols with associated types are more difficult to use in practice. First of all, when it comes to implementing such protocols, only one concrete type can take the placeholder's place. That means if you want to merge collections with strings and collections with integers, you'll need to have two separate implementations. Again, you get in two highly specialized tools. But the challenges with associated types don't stop here. Using such protocols as existential types was entirely impossible in the past. And even now it comes with significant restrictions. I'll explain existential types in the next video, but in short, it's when you use the name of a protocol as if it were a concrete structure or class. Protocols don't really work this way, but Swift sort of bridges that gap for your convenience. That's how you're allowed to use protocol names as property or parameter types. Normal protocols and protocols with generic methods can be used like that pretty easily and with no limitations. But protocols with associated types take much more thought when you design the system as a whole. I'll show you what I mean later in this video. But before that, there's one more topic I want to discuss. As you can see, associated types make your protocols more flexible and reusable. They offer placeholders, and objects which conform to such protocols replace those placeholders with concrete types. Effectively, the conforming objects can decide for themselves what type they will support. But what if you want the conforming object itself to be a placeholder? I think it's easier to see with an illustration. Let's say I want to have a mechanism for duplicating objects. I can declare a duplicator protocol for that. But as you know from this video, duplicating objects isn't always a straightforward process. For example, copying class instances often comes with unintended consequences. Plus, you'll have to decide when you need a deep copy or when a shallow copy will do just fine. Because of all that, a universal duplicator implementation won't solve the problem entirely. Perhaps I'll need to have separate components for duplicating different types. One approach is to declare an associated type that represents the object being duplicated. This associated type will be used as both the parameter and return value of the duplicate method. With this protocol, I can implement individual duplicators for each type I want to make copies of. I can create duplicators for different structures, classes, enumerations, and so on. Each of them will know exactly how to make copies, because they know what type they're duplicating. But you probably see that this approach isn't very convenient. Whenever I want a copy of some object, I need to instantiate an entirely new component and pass the existing object to it. Ideally, each type should be able to produce a copy of itself. So, instead of using an external duplicator, I want the object itself to have a duplicate method. I want the object to conform to this new duplicable protocol. But how do I express the relationship between types now when I no longer have an associated type? This is where the self requirement comes into play. The self keyword is more or less equivalent to a normal associated type, except you can't really choose what concrete type it will stand for. That's because self refers specifically to the type of the conforming object. So, for instance, if my duplicable protocol is conformed to by a string, then the duplicate method will return a string. And if some class conforms to that protocol, then calling the method will produce a new instance of the same class. Protocols with the self requirement have the same restrictions as protocols with associated types. I'll demonstrate them later in this video. But before I do, let's briefly discuss how you make a choice. As you can see, associated types are really powerful and flexible. But with those power and flexibility come a few restrictions on how you can use such protocols. Because of that, using associated types makes sense when you need to clearly define type relationships between multiple protocol methods. For instance, let's say all methods of your protocol must work together on values of a single concrete type. In that case, you'll avoid a lot of boilerplate by using associated types. However, when your protocol methods don't really depend on one another, or when some of them don't even need abstraction at all, then associated types might be an overkill. In that case, generic methods will let you use simpler syntax, while still providing enough flexibility. But generics, associated types, and nearly every other tool that's available to you, they're just that, tools. In most situations, they can work in combination and complement each other. So even though it often seems like you have to make a choice, in reality you can mix and match different tools any way you need. And the following demo shows just that. So, for this practical exercise, let's say you want to build a component which multiplies an object by a number. What multiplication means specifically depends on the object itself. For instance, multiplying a number works just as you'd expect. And multiplying a string means repeating it a given number of times. For now, let's just focus on these two types, strings and integers. Without generics and without associated types, you'll have to declare two separate protocols. You'll also have to implement them separately, although it's worth noting that the same object can conform to both protocols. But this approach is neither flexible nor scalable. The protocols are incompatible with each other, and if you want to support another data type in the future, then you'll have to repeat every step manually. Let's see how we can improve this design. Using generics, you can declare a single protocol. Doing so gives you a nice and elegant interface, and you can use it with any data type. Problems begin when you try to implement the protocol. The generic parameter has to be checked and cast to a supported type at runtime. So far, nothing terrible, but that's because right now you can multiply only strings and integers. But if you add support for more types, this construction will grow even uglier. Okay, let's try to start over and solve this problem with associated types. Instead of a generic parameter, you can declare an associated type O for the object. Then you've got two components which conform to the protocol, and each of them deals with just its own concrete object type. If you add another type in the future, you'll need to implement the protocol once again. While it doesn't seem like a perfect situation, it's actually not that bad. That's because you still have only one protocol, and you don't have to change any existing code. But can we find something better? Think about it for a minute, and tell me in the comments. I'll present you my version a bit later, but before that, let's take a step back and have a look at how we use the protocols. The beauty of protocols is that to use them as another component's dependencies, you don't really need to have functional implementations. Imagine you've declared all the 4 protocols, but haven't implemented any of them. Now you're working on a new object, and it should call the multiplication methods. With the plain protocols, it's really easy. You just specify protocol names as the types of properties. After that, you can call the multiplication methods directly, as if they were defined on a structure or class. In other words, the protocols are used as existential types. This is possible even without having an implementation. That's because each of the protocols clearly tells the compiler what type it supports. In that case, the compiler can verify that you're not trying to give it something else. The downside of this approach is pretty obvious. Managing the different flavors of multipliers becomes the job of the client object, meaning the object which uses the protocol. If at some point you introduce another multiplier, you'll have to declare a new protocol, implement it in a new object, and then update the client. It's not very convenient, right? Using the protocol with generics is much easier. You declare a single property, and again you can call its multiply method directly on this property. What's even better is that you can call the same method with parameters of any type. While the plan is to support only strings and integers, resolving the parameter is the implementation's job. And for now, you don't have any implementations, so nothing to worry about. And again, the compiler has no problem with that. While it doesn't know our plans, it relies on the generic parameter to type check the code. This generic parameter has no restrictions, so the compiler assumes that the implementation can handle any value. And now let's see what we have with associated types. The first thing you'll notice is that you can't declare a property the same way as before. This time, you'll have to use the any keyword. This keyword was introduced in Swift 5.6, and it's actually meant to transform protocols into existential types. But in this case, it still won't help you. Let's see why this happens. In the previous 2 cases, I emphasized that even without the implementations, the compiler had everything it needed to type check the code. But now the protocol declaration alone is not enough. The compiler can't verify that the integer or string you're trying to pass is actually supported by the protocol. In a way, protocols with associated types remain incomplete until they're implemented, and until the associated type is specified explicitly. And that is why you can't use such protocols as existential types like that. To fix this, you need to resolve the ambiguity, and you've got more than one place to do so. One of them is the client object. You basically have to de-abstract the protocol by fixing its associated type in place. You declare a new protocol, and you use this where condition to tell the compiler that the associated type will always be an integer from now on. Then you repeat the same steps for strings. After that, you go back to the first option that I showed. As a result, you get to use the protocol as an existential type, but at the cost of having more code. By the way, I'll be explaining this where construction in the next video, so don't forget to subscribe. Another way to resolve this situation would be to eliminate the use of associated types entirely. You can declare a new protocol with a generic method, and its implementation will use concrete types directly. I won't stop here for long, but here's the code. And as a final alternative, you can simply pass this ambiguity up the dependency chain. This involves using the protocol as a generic constraint, but I'll save this big topic for the next video. For now, I'll only say that while this approach doesn't look as nice as existential types, it offers huge performance benefits. But now let's go back to the question I asked. How can we improve the software design in the first place so we don't have to deal with problems later? I'd love to read your ideas in the comments, and here is my suggestion. I would move the multiplication to the actual object. For that, I'll declare the multiplicable protocol. This protocol is gonna have the self requirement. As for the multiplier, I'll declare it as a protocol with a generic method. But the generic parameter will have a constraint. Specifically, only types which conform to multiplicable can be passed to this method. Implementing this method takes a single line of code. Essentially, it delegates the multiplication to the object itself. And here's the result. I can multiply strings and integers, and when I want to add support for a new type, I just have to conform it to the multiplicable protocol. I need no changes in the protocol, its implementation, or the client component. The downside of this approach is that I'm extending built-in types. While I don't believe it can backfire in this scenario, this is still something to be aware of. Let me know what you think of my idea. And now it's time to wrap up this demo. In this video, I've had a look at a few protocol topics beyond the basics. With generics, associated types, and of course extensions, your protocols become powerful enough to solve really challenging problems. But the most interesting stuff is still ahead of us. In the next and final episode on protocols, I'll explore a few advanced level topics. They include method dispatch, bridging protocols to and from Objective-C, and using protocols as generic constraints. Those topics are sort of a grand finale of this mini-series on protocols, so I really recommend you to subscribe and stay tuned. And if you found this video helpful, your thumbs up are very much appreciated. I'll see you in the next video. Until then, make your extensions fly.